actually record this. So, strongly connected components are basically where we can kind of merge a single graph into multiple nodes. The two nodes are connected in a directed graph if there's a path from one to another, right? So A and B, we can define them as not really being connected in a directed graph sense because we can get from A to B, but we can't get from B to A. Now these two are connected. And in fact, we can get from one to the other, and we can essentially get from one to another, and back again. We can travel freely between A and B. They can't be pulled apart. Right? And the idea here is that connected components, right, are basically the parts of the graph that can't be pulled apart. So you can get freely from A to B, and you can get freely from C to D, but you can't get from it but you can't get from one connected component. You can't. A and B and C and D are not connected, right? You can get from one to the other, but you can't freely travel between them. So we can actually kind of graph that graph, okay, as kind of and this is what we're referring to as the metagraph. All right, so the idea here is that you do depth first search on them, and so what it is that every directed graph is a DAG of its strongly connected components. Basically, we can turn any one of these graphs into a directed acyclic graph of the strongly connected components. Okay, and then let's see, did it have the algorithm here? Or does it say what to do? So when doing DFS, okay, run the strongly connected components algorithm on that. Okay, did it say what the algorithm is? What they want? Did they talk about it? Or so let's see. If they explore, then therefore, if we explore a node, node highest post depth and the depth for search must lie somewhere in. If C and C A prime are strongly connected component and there's an edge from those two, then the highest post number is bigger than that. So the highest post number in that is bigger than that. Okay, so it says the strongly connected components can be linearized by rearranging them in decreasing order from their highest post number. This is a generalization. Property 2 helps us find the sink, which says that the highest post number is the source. And then and then A, to get the source, we reverse the edges in the graph. Oh, there it is. Yeah, it's on page 94. Okay. So the resulting algorithm is reverse the graph, run depth first search, and run the undirected components algorithm from section 3.2.3. Using the depth first search, process the vertices in decreasing order. So, okay, let's go ahead and do that let's go ahead and check out this first graph, okay, the graph in our initial graph in our textbook. So A to B to C, so A to B to C to D to E. Actually, what am I doing? Why am I just pulling that up? Let's see. I have slides. It's like, okay. So documents. Chapter 4, paths. That's paths. Chapter 3, graphs. Okay. I'm like, it's here. Okay. So there is the graph I was talking about. Okay. So we can create this metagraph fairly easily just by us looking at it, but how do we figure out what the strongly connected components is? The idea here is, so 3.9. So what we do, so how do we create this? Okay, run def for search on the reverse of the graph, and then run the undirected components algorithm. So let's see. So decomposition of it. Okay. So what we do is that we are going to, so here's how that works. We run DFS. What we do is that we reverse all of the, so what we do is that we generate, so we take our graph here. So let's take a look at the graph. So see, we've got the strongly connected components circled here, okay? And you see how they're how each one is defined as a strongly connected component, right? They are the ones that basically you can freely travel between each other. So the first thing we do is reverse all the edges. Now that doesn't change what the reversely connected components are, right? The strongly connected components are, right? Because if you can get from one to the other, flipping the edges is not going to change that, right? So you see, so let's look at this subsection, this big subsection here, GH, I, J, K, L. And notice how the arrows are all flipped in the reverse of the graph, but you can still get from, right, we can get to G to H here, but you can't get directly to G to H, but there's still a path. Okay? So, there's a fly. So, okay. So we've got that, and so you still get that metagraph. So what we do is that we are going to run def for search on this graph, specifically this graph over here. All right, and there's only one place we can really start it at, which is L, I believe, or rather. We can only start. We have to start it at this first strongly connected component. All right. So what we do is that we are going to generate our pre and post numbers. Okay. Pre numbers we'll write them down on the left, and then the post on the right. Pre and post meaning what happens as we enter it. So let's start at G. So that's 1. So follow this 2, 3. Okay, and then 4, 5, and then 6. So we're just following def for search's algorithm, which is that we keep exploring nodes. All right, so here I'm just trying to see. Do I have a choice here? 7, yes. Now we're gonna break ties alphabetically. So 8, 9, 10 is A. We're done there, so this is 11. We're back to B. Let's see, yeah, B can go to E. That gives us 12. All right. And then can E go anywhere? It can go to B, but we've already bid to B, so we can't go anywhere new from that. So 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22 over there. Okay, and now we're done. So it says that what this should give us is, if we run def for search, we get, let's see, run def for search on that GH. Okay, but how do you get to D? D doesn't get there. Run def for search. So G, the decreasing post numbers in the def for search of GR are, it says, in decreasing number of these are G, I, J, L, K, H, and then it does C. Why does it say C, F, B, E? Yeah. So I'm just trying to say, so why is that there? So run this algorithm on the graph on figure 3.9, or it's saying to do it. Hold on a second. GH. Yeah, even if you ran it on the one in 3.9, you can't get from GH to, unless DFS, oh, right, give me a second. Graph on 3.9. This is so weird. Why is it saying 3.9? So, what's it saying? Yeah. So graph G, oh yeah, it's got everything over here. So it says, here's the reverse of the graph. Okay, we run this, step 1. Okay, and then it says D in the graph. Run DFS on this, but you can't run DFS on this to get from here to D. That just doesn't work, right? Unless I'm highly mistaken, right? Because D is connected like this. Okay, run DFS, the undirected connected components on this. Okay. Therefore, we can keep the post numbering from our initial DFS to successfully out the second strongly connected component, the third. Okay. I don't know why they're saying this. I'm following the algorithm, and I'm very good at following algorithms. It's what I do. Like it said, run DFS on this. I did run DFS. Unless I'm missing something over here, which is explore, which says visit, and DFS says, hey, DFS, come on, which is if not visited, for all vertices, if we've not seen it, explore, which means that we would eventually start that, we would eventually go to D, but we can get from G to, if we start at G, we can get from there. I'm really not sure what they're getting at, because they say run it on this with all the edges reserved. So if we do DFS on this, the highest post number will come from a source, from a strongly connected component in graph, which is to say the sink is a strongly connected component in this. Once we found the first strongly connected component and deleted it from the graph, the node with the next highest priority will be, among those remaining, will be whatever remains of G. Therefore, we can use the initial post numbering to successfully out. So here, run DFS on G. I mean, because the next step should be to basically do, because the next step for this would be, according to their algorithm, is that, okay, for every vertice that I haven't, let me just see, double check this. Depth first search, if we've not visited, for all vertices, if not visited, explore from there. And to explore, you basically see what's reachable from explore. So you would go, so here we would go 23, 24. At least that's what I would think you're supposed to do. So highest post number is a, okay, so whatever the highest post number will be, will belong to a sink. Once we found the first strongly connected, deleted it from the graph, the highest. Yeah, I'm wondering if there's incompatibility between this, because or if I'm missing something here, because that is fairly easy to pull apart. I mean, like, all right, let's take a look for the one from the book then, for that one, right? Right, run the strongly connected components on the graph in its reverse, right? Now, one shows the graph, right? On the following graphs. Okay. When doing DFS on, so, okay. 1, 2. Run the strongly on the following directing graphs. 3.2.3. All right. Unless, hold on. I see what happened there. Okay. So run GFS on graph on the reverse of this graph, it says. Okay, here's the reverse of the graph, and its starting point wasn't G. Its starting point was A. They start from A because that's the first one. Okay. Now I understand what they're doing. Okay? So here we go. Here's the reverse of the original graph, right? So what we're going to do with this is that we're going to start with the node. We're going to explore all the nodes in alphabetical order. Okay, we're going to do DFS on this entire graph to figure it out in alphabetical order. So this would be 1, and then we can't get anywhere from here. So 2. Okay. Next we look at all the unexplored nodes, pick the highest, the one with the first name. That's B. 3. So do DFS from 3. Sorry, from B. 3, 4, 5, 6. Make sense? So the next node, and then let's see. So A, B, E, and then C, which is 7, 8, 9, 10. Like I said, sorry, I've had a busy weekend, so I haven't had the chance to review. I thought this was something already covered. Okay, 5, 7, 10, and then let's see. So down D, which would be 11, 12. Okay, and then what we've got here is the next node we need to explore is 13, 14, 15, 16, 17, 18, and then the important numbers are 19, 20, 21, 22, 23, 24. List the nodes now in order. Step 1 is saying list the orders now from least to greatest. Okay, which would be G, I, J, L, K, H. And then the next one is 19, then 12. We're listing them by post numbers, so the second number. Make sense so far? So D, and then the next one would be C, F, B, E, and then A. Make sense? So that's how they get this order, how I got this ordering, because they were starting DFS not from G, but from A.
Wait, so we listed in decreasing order?
Yes, by the post number. by the post number, right? 24 was the biggest post number there. Okay, so now what we do is that it says step 2, run the directed components graph algorithm from section 3.2.3, and during the depth first search, process the vertices and decrease. So now we run this on G, the original graph. On the original graph, we run the undirected connected components algorithm for section 3.2.3 on G. 3.2.3, which says a new connected component. So these regions are called connect. Each of them is a subgraph that is internally connected but no edges to the remaining vertices. So all right. Let's see what it says. So, we start from here. Now I see what it says. So now we use this order, we now use this as a guide. We start at G, okay, and then do DFS. So when we do DFS here, we go 1, 2, 3, G, H, I, G, H, I, J, K, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and we've listed these numberings, but we don't really need it because we're already back here. So what we do here is that we're going to refer to all these as connected component number 1 because we explored all of them and we can't get to any other. Now we go, and so that's how we split them up over here. Then we start from D, and we can't get any from D. Then C and F. So then we start from C and we see we can get to F, and then B to E. We see that's a connected component by exploring from B and E. You see how this is working?
Sir, like in the when we were doing it in the reverse graph, why do we go to the D first instead of G?
Because D comes alphabetically first.
Oh,
okay. That's what we were doing for this.
Do we have to do this when I can just see what is strongly connected, what is not?
I mean, the idea here is for we want you to run the algorithm, in which case, what order are the strongly connected components found? So let's look at this from on 1, okay? 1 gives us we have A, C, D, E. I mean, what am I doing here? I can, give me a second. Das, Guptas. I should probably just go ahead and download it. Download. Save. So for this one, this is page 96.
so we always start with A.
Yep. So let's go ahead and see this one. So easy enough to reverse this graph, right? So whenever there's a choice of vertices, always pick one that's alphabetically first. So, thought I said to open it in. Here we go. 96. Sorry. I realize I can't draw on that unless I'm an edge. So, okay. Let's go ahead and overwrite. And what I'm going to do is I'm going to write over these because you can draw on electronic books. That's a bit too thick. Okay, nope, wrong way. There we go. Let's go ahead and do that. So I think that's fine. So, no, that was a mistake. Should have been able to figure out that was a mistake. Okay, so I guess go thin as possible. So, all right, so we reverse the edges. I know that gets confusing. I'll use a different color for my yeah, for my post and pre. Okay. Okay. So, okay. So we're going to start from A. So we're going to, sorry? H to F? Yeah, A, well, it says to break ties alphabetically, so 1. Oh, I missed one from H to F. Okay, I'm like, why were you going from H to F? No, we're not going from H to F. What are you talking about? So there we go. Yeah, I could spend some more time doing this better if I needed to. You know. That makes matters a bit easier to see. But we'll go ahead and get started anyway. Not waste too much time on drawing. So, okay, so we started A. A can go from A, or we can go from A to either B or E, right? So we're going to go from A to, so we're going to go from A to B. Okay, so it gives us to 2. And then from B we can't get anywhere, right? Because we've reversed all the edges, so and we can double check that for ourselves. So 3. Then from 1 we can go to E, right? What? E is 1. So yep, it's 4, comma 5. Sorry. I know I'm going slow. I'm just having to double check everything as I do it. 4. Can't go from anywhere from E. 5. 6. Okay. And then we can't go anywhere else from A, right? And so, yep, we'd go now we're going to go to C. C, we're going to see we can see the strongly connected component actually because it's pretty well strongly drawn. Okay, so 7, 8, 9, 10. Okay. So now we need to, and then we get over here to C, and we can't, and there's nowhere else we can get from C. So 11, 12. So now, interesting, we don't write 13 here because we can get to H, right? So 13. H can go to I, 14. This can go over here. J is 15. Okay. Interesting. So F. We're doing this right because
H can also go to A. No, it can't.
So D to C shouldn't be a TH.
C to
D to C shouldn't be a TH because C is already weighted. It's
oh.
It's a, what do you call that? It's a bracket.
Well, okay. Let's back up for a second then. Okay. So we're here at 7. Okay. Right? 7, 8, 9. And we have 2 choices of where to go. We can go to D or we can go to H. And yes, you're right about that. D or H. So H, so D we can go, so 8, so we can go from here, 7, so 10. 10. Okay, and now we're at 10. We can't go to C, right? C is already there. So yes, what we do is 11. Now we can go to H. 12, 13, 14. Okay? And now we can't go anywhere from there. So 15, 16, 17. F says 18, 19, and then 20. So now we list them C, J. Okay, I see how this works. C, J, F. So C, J, F, H, 17. Why did I write 17? Right. H, I, G is 15, so G. And then, what was it? D is 11, right? 11, no, D. Why am I? Okay, D. And then we've got E, B, and A. Okay, so we've identified all these. And guess what? This is all useless now. Or rather, all this drawing that we did over here is useless. But the ordering we got is not. We're going to actually keep that ordering up in case we need to refer back to it. And now we look at the original graph. Okay? Make sense? So now what we're going to do is, this was 12 over here. So now I'm going to choose another color. And we do yet another DFS. So in what order, and so we're going to be able to answer A here. Okay? In what order were these strongly connected components found? So we start at C. 1. So 1, 2, 3, 4. Okay? 1, 2, 3, 4. And now we can't get anywhere from there, right? 1, 2, 3, 4, 5, 6, 7, 8. Make sense? Okay? So now let's cross off. So now let's write down C, D, F, J. That's our first one. C, J, D, F. I don't know why I said A. Okay. Next one. So now we look at this list that we've got here and select the next thing to attack from the ones that we haven't crossed off. Because, again, what we have to do is over here look at the correct components. You'll see how that this is working. So that's got 1. H gives us. So now if we go to H, that would give us. Well, yes, was looking 9, 10, 11, 12, 13, 14. Again, we can't go anywhere from there because of the way this is ordered. Because of the way it was reversed, we were going from sinks to source. Sorry, from sources to sink in the reverse, which is effectively the same as going from sinks to sources in the real one. So H, I, G. And then we can look at E, how that's just hanging out by himself. So H, I, G is 2. E is 3. Yeah, talking and trying to write at the same time is silly. E is 3. Don't have to even write the rest out. 4 is connected component 4 is B. And then connected component 5 is A. So it has 5 strongly connected components. Right? So now so what is the sources and what's the sinks? Well, the source, let's see, the sources have no incoming edges.
B.
So, yeah, the sources have no incoming edges, but why would it? The receive source, so yeah, that finds it. Yep, so our sources are going to be B and E. Those are sources. And our sinks had the highest, our sink had the highest edge in the, sorry, had the highest DFS in our original one. So that was, so this is our sink over here. Okay. And then
What was
the sink is C is here because all other routes eventually lead into here and you can't escape from it. Right? You eventually, yay, being able to use multiple markers, right? Okay. Okay, eventually all routes get into here. Oh, it's not liking what I'm doing. All routes get into here and you just can't leave from it. Make sense? That's why it's a sink. But we were able to find it because we've grouped them accordingly into connected components.
So what's the source?
And technically, A should have come first in those. Technically, A should have come first because it had a higher count than B and E did. I messed up here. A should have been over here because it had a higher green one in the reverse. So I messed up there. So that should be 3, 4, 5. That's why I was kind of confused. I'm like, shouldn't the higher numbers be the sources? So a source is basically the parts that have no incoming edges. Basically, think of it as like, think of it literally as water flowing. Okay? Water comes from a source and it goes downhill. Once it goes downhill, it can't go uphill, right? Unless there's some very extreme conditions, I don't think.
So sink is something that would have outflow.
Yeah, sink is basically where basically all the water kind of goes into. It's the water sinks down to this level. Think of it as flowing water in terms of source and sink. And those are terms that, and all directed acyclic graphs have a source and a sink. We're pointing out that this thing over here isn't a directed acyclic graph, but the strongly connected components are a directed acyclic graph. Make sense? So if I now draw that metagraph over here, okay, and there's your metagraph. I know it's ugly as sin right now, but again, I'm doing the best I can with being able to draw on top of stuff. Okay, now I like 4. What's the minimum number of edges you need to add to make this entire graph strongly connected? And the answer is we have to make sure that each of the connected components are strongly connected, right? So we would need to add, so let's basically be greedy about this. How can we make G and H strongly connected, right? We can make G and H strongly connected by adding an edge right over here, right? And that adding that edge would make the entire thing strongly connected. Those 2 segments, right? Now we have these other outlying segments, but the same thing. To make it strongly connected, we add in another edge to make it strongly connected. Adding edges over here to make those 2 strongly connected is not a good idea, right? Between B and E, because there's nothing there. We're creating something from nothing. But adding paths like this, suddenly it's all strongly connected. So what's the minimum number? Well, we had 5 we had 5 nodes, so it turns out it's 4, right? It's n minus 1, where n is the number of strongly connected components. I can count, I swear. It's just it's my training in me that says you got to reduce it into an abstract number as much as possible, right? All right. So we were answering question on the fourth part of that. So here, right, I've circled the strongly connected components in yellow. Okay. Yeah, I know it's ugly as sin, as I said when you left. So I've done the strongly connected components here in yellow. Okay. And part 4 and part D of this question was the minimum number of edges you must add to this graph to make it strongly connected, right? And the answer is 4, and those are the red edges we can add. And now if we add those red edges to the graph, you could get from any of those subgraphs to any other, or those strongly connected components to any other.
Was there like B to G and B to I and all those?
Well, if we add this, then we could get from B to E by going through A.
Oh.
Because if it's strongly connected, you can get from one to the other, and from the other to one. From any node, we could get to any other node. So by adding those, the graph would be fully connected. So we can kind of conclude from this, or we can kind of hypothesize, and if we worked at it, we could probably prove that if that the number of nodes we need to connect things is the number of strongly connected components minus 1. Sorry, number of edges to need to connect, right? Because they're strongly connected components, meaning that one arrow leads to the other. And it doesn't have to be, and I mean, we can just see this with other edges too, right? This isn't a unique solution, right? We just need to connect them to the other. So like here, we can instead do, let's see, instead we could do this. So from here to here, from here to here, from here to here, and then, yeah, from here to here. And now we can get from anyone to anyone else still. So we can get from A to B by going through here. We can get to B from here by going through here. We can get to B from anywhere else. So you still have got number 2 to solve on your own. But I think but you guys understand how this works?
Yes.
Okay. Sorry it took so long on that.
Wait, what is between B and E?
What was between B and E?
Yeah, that red pencil, what is it?
Oh, that was just saying that I don't want to bother adding anything between B and E. I want to try to connect those two, because I don't want to try to add edges that way, because that's more work. I'd have to create 2 edges rather than 1. Make sense? That was just me scribbling out like an idea. And I left it in. All right. So, I was going to say, so I want to do Bellman-Ford on tomorrow's quiz, but I think you also need a break. We've been doing this for a while. We've spent, well, and that's fine. So do you need a small break before we cover Bellman-Ford?
Yes.
Okay.